I don't have any formal connection to the IOA, but it's wonderful to be at this party. And I think I'm also the only one that was not given any remit on my talk. I was just asked, do you want to give a talk? I said yes, and then it just appeared. I sent something in, they accepted everything. So I can talk about anything I want. But I will be talking about high redshift 21 centimeter cosmology. I will give a very broad overview of this field, but of course focusing also on the work that we've been doing over the last 20 years. Now, this is really a field at the frontiers, right? We've collected petabytes of data, and we only have upper limits, right? Your signal to noise is our noise to signal. So, and of course, we have this wonderful data coming in, right, from JWST, just an example here, what we've seen over the past few days. And this is really tremendously exciting. But these are really only little fireflies in the forest, right? These are highly luminous galaxies, and they really form the tip of the iceberg in a vast sea of neutral hydrogen. And what we try to do is to see that sea. Right, so what can 21 centimeter cosmology tell us? So the ultimate goal is to connect these 21 centimeter observations, once they are successful, of course, right, to the underlying galaxy properties. For example, the ones I just showed, right, to find that connection. But that connection is, of course, on very different scales, right? These galaxies are tiny and puny, and in terms of volume, don't occupy a lot of volume in this enormous sea of neutral hydrogen. So that's a topic on its own. I will not talk too much about this today. It is a very difficult and ongoing journey that I will show, right? I started this in 2004, right? And we're 20 years down. We've collected petabytes of data, as I said. But we're making steady progress, and I will show that today. So I'm pretty confident that in the next few years, and certainly with SKA on the horizon, we will make a detection. And in light of the LHC, right, when they were going after the Higgs boson, right, the director of CERN, as far as I know, said, whatever we're going to detect, we're going to call it the Higgs boson. So with SKA, whatever we're going to detect, I'm going to call it the epoch reionization. So, okay, let me move on. So the idea is the following, right, that we detect, of course, the 21 centimeter at high redshift, right? We follow the gas density, not just the gas density, of course, it has spin temperature in it and all kinds of other stuff in it, and then infer from it all these wonderful properties about the gas, but also about the dark matter, and connect this not just to the underlying galaxies, but of course also to cosmology and do fundamental physics. And that's where I'll come to at the end of my talk as well, where the term moon in my title plays a role. Right, so for those not familiar, right, what we measure with the radio telescope, right, we try to go after that 21 centimeter, is a brightness temperature, with actually in contrast to the cosmic microwave background radiation temperature. So, and it's actually made up of, if you expand it into a whole bunch of terms, like the ionization, of course, the baryonic density fluctuations, some cosmological parameters, but also the spin temperature, which couples to the gas temperature, radiation, etc., and also peculiar velocities, which you can measure if you have very high signal to noise. So the whole name of the game is to measure this as function of space and frequency, therefore redshift, so also time and also a third dimension, and invert this, generally via models, of course, to learn something about cosmology and astrophysics, gastrophysics. So to invert this equation. This is just a simulation of a cosmic time, a slice through a simulation of the brightness temperature and how it evolves over cosmic time from the dark ages, very high redshifts, where you have very few fluctuations, but you have a signal in absorption here. So it's below black here, red. And then at some point you get fluctuations, you get ionization, and at the end of ionization, of course, most of the neutral hydrogen is gone. So what we hope to do ultimately is to measure these fluctuations as function of space and as function of time, and also measure the global average signal, which again I will not talk about much today. right? So this is still something I often show on how you, when you change the underlying astrophysical parameters, this is a movie by Andre Messinger and Greg, how if you change those parameters, the signal changes. This is the global signal. So you can really see if you change the underlying astrophysics, the signal changes. So that also means you can invert it and learn something about it. And also the variance here, so this is the power at a given k-scale of 0.1 changes as function of redshift, but also as function of the astrophysical parameters. You can combine this with luminosity functions, for example, from JWST. This is still just from HST, and then, right, via current codes, like 21 centimeter fast, learn something about the astrophysical parameters by combining the future measured power spectra, for example, with these luminosity functions. So this is also a slide I often show, probably have shown it for the last 20 years, right, on all the things you can learn in general categories as you go from the dark ages to reionization. And we're currently really in a phase that we're trying to probe reionization. The instruments are sensitive enough in principle, right? It's all about systematics, not about signal to noise anymore, to measure reionization. But there are already instruments now, like Nanofar and Hera, that are starting to probe the cosmic dawn. For the dark ages, we really have to go beyond Earth, so really have to go to space and the moon. And at the end of my talk, I will quickly talk about this. And there are various things at these various eras that you can learn about the universe. So, but most of the focus with the current generation instruments is on reionization and somewhat on the cosmic dawn. So I will just show a few slides, but I think maybe Eloy later on today, I think, might show a little bit more about this, about global 21 centimeter experiment. So if I go quickly back here, you can take a volume average and just get the brightness temperature of that thing. So you can do that over the entire universe with a single dipole. Not the entire universe, but at least what that single dipole sees. So that's about half the universe. And take an average. And actually, you can measure that signal, if it were not for systematics, within a day at the cosmic dawn. So even a single dipole can do this. Of course, it's all about systematics because the foregrounds are 6 orders of magnitude brighter. But, of course, there are people, many people, that are brave, like Eloy, that are doing this with these sort of single dipole experiments around the world. These are a couple of them here that, as far as I know, are active in doing this. And, of course, Edges in 2018 put out a paper claiming for the very first time a detection. Now, of course, this is highly debated because the signal was not just a little bit odd in shape, but it's also much deeper than you would expect in a standard sort of model, about a factor of 2 deeper than any model can explain. So, of course, that immediately spurred a lot of exotic models, right, coupling to dark matter, which is much colder, etc. And also maybe more radio background, which can, of course, also increase the signal because you're measuring the 21 centimeter absorption against a radio background, in this case the CMB. But if there's a brighter radio background, this signal becomes deeper. Now, this is still being debated. It's not excluded yet, although the Saras experiment has put out a paper a few years back where they exclude this at the almost 3 sigma level. But there are also debates about this result. So the jury is still out. We're also waiting for Edges 3 results to come out, and of course updates from Saras as well. Of course, if this is true, it would be fantastic because we immediately know that the standard model, or at least the way we think about the universe there, is incorrect. As I said, I will be short about that. I will talk a bit more about 21 centimeter power spectrum experiments. Right there, we don't take a global average. We actually look at the fluctuations as function of space and its function of frequency. And that frequency you can look at in 2 different ways. Right? It's redshift and therefore time, so you can look at evolution. But if the box is small enough, you can also interpret it as a 3rd dimension. So you can actually make power spectrum in principle in 3 dimensions. You can measure also peculiar velocities. Now, if your signal to noise is strong enough, ultimately, of course, with an interferometer such as the SKA, we can do tomography and look at the bubbles in the ionization regions individually, or at least the largest ones. And here, there are also 6 active instruments. This is LOFAR, the one that I'm working mostly with, including also NanoFAR. These are the 2 that I will talk mostly about. MWA is in Australia, LWA LADA in the US, GMRT in India, NanoFAR is in France, and HERA is in South Africa. And the good thing is, right, we're all trying to find the road to Rome. We haven't found a way to detect this signal yet. It's all about systematics. So all of these instruments, as you can see, have slightly different layouts, have slightly different instruments, have different philosophies, etc. So, right, we're learning from each other also what to do and what not to do, where the errors come from, what dominates the systematics. So this is just again, a single slide giving some selected key highlights or results, mostly the deep limits from each of these that have so far been published. And I will come back to this in probably the next slide. Yes, this one. So just as a take-home message for now, this is where we are, right? So these are some models here, these dashed lines from 21 centimeter fast. The details are not that important. But as you can see, at least at the lowest redshifts, over the past sort of decade when the first results from the GMRT came out, the limits have really drastically reduced by 2 orders of magnitude or more. And this is often with the same amount of data, the same number of hours. This is purely reducing systematics with the same data. For example, the results that I will show in a moment here are taken with about 140 hours of data, but this is about 5% of the data we have. And these limits will go down linearly with integration time. So we could go down by a factor of at least 20 or so more. So we will get in that region, hopefully, in the coming year or 2. I will also show a bit about high redshift. Now you see, right, the limits here are much, much higher, and that is just because the thermal foreground, the noise is much, much brighter, much higher at lower frequencies. So things are much more difficult at higher redshift just because the galactic foreground is so much, much more bright. So as I said, we'll give a sort of broad brush overview and also an emphasis on the things we're doing. So we'll show a few key results from the Codex program, which is a program I'm the PI of, that uses LOFAR in various ways, but also NanoFAR, and also tries to initiate a new program on the moon. Now, of course, this is something I'm doing with a large group of people. This is some of my team here, and this is a meeting we had last year on this topic as well, and I think Martin is over there. So, and of course, not everybody is still in this picture, but it's certainly not something I'm doing by myself. So with this program, we try to really cover that redshift range and connect all of these instruments, the things we learn, the software, the systematics, right, to learn a broad view picture of how to move forward in this field. Right, so we're working with NanoFAR, with LOFAR, as I said, but we're also preparing for the SKA. We're using LOFAR in a different observing mode that I will not talk about today. And again, we will also are preparing for a space-based mission in the coming decade. And again, these are the instruments that I already mentioned, LOFAR, NanoFAR, the SKA in the future. But also I will quickly show this one and a future instrument. And they're all covering different redshift regimes. So this is, well, at least what we see from LOFAR. This is an instant image as seen with the ARTFAC instrument. It's basically an all northern sky field of view instrument. So this is just a snapshot. You see the Milky Way here. You see the bright sources that have been subtracted. Now, our primary fields are the NCP field, the North Celestial Pole, and the 3C196. Now, why did we choose those 2 fields? This field here is stationary in the sky. It's visible all year. If you point at it with a phased array, your beam doesn't change. So those are nice properties. The disadvantage is there that RFI can accumulate there if you have it, because it's a stationary point in the sky, and RFI on the ground is also stationary, and 3C196 has a bright calibrated source. And both, so this one is a little bit more sensitive, but has a bright source in it for calibration. This one is a little bit less sensitive because it's a bit sort of under a larger angle, so you lose sensitivity with the phased array, but it's visible all year round. So we collected about 2,500 hours of data here and about 1,000 hours of data here. And with NanoFar, so the French telescope, we also cover the NCP field, and we are now covering other fields that are not indicated. With ARTFARC, we cover everything that has an image here, and with, of course, this space-based or lunar-based, we will cover whatever half hemisphere or part of the sky you can see from the moon. So first I will talk about LOFAR. For those living under a rock, this is LOFAR, at least seen from space. The inner part, this is called the SuperTerp here, or the six-pack, because it has 6 stations in it. We are using for reionization of the higher frequencies these boxes here that have, each of these boxes contain 4 by 4 dipoles. And so we're using mostly these here, but also the ones closest. So we're using these very short baselines because they are most sensitive to the large scales. And we build up most signal to noise on those large scales. So the larger, longer baselines are only used for calibration, foreground removal, control of systematics, etc. Now you also see those individual dipoles here. These are the low band antennas, which we have used for the ARTFARC experiment, but again, I will not talk about it too much, but it focuses more on higher redshift and cosmic dawn. But since we now have NanoFar, NanoFar is much more sensitive. That will be the focus in the future for us. So what do you see if you observe such a field? So this is again the image I showed before, now in a different projection here with the NCP, and if you zoom in with another observing mode, you see that, well, this is what you see, all these bright sources here. Of course, these are the point spread function side lobes, so that's expected. But actually what we only analyze, because we're observing with LOFAR in a beamform mode, is this inner 3 by 3 degree square here. Now that has enough signal to noise to get us a detection. So you think, why don't you use everything? Well, I can explain that offline. Right, we use this. This is about the size of our primary beam. Now, of course, it has very bright sources in them, so we need to subtract those. So that is what we spent the last 10, 15 years developing, is pipelines to remove the bright foregrounds with their direction-dependent calibration, right, all the gains, polarization, everything we take along. I can talk for hours and hours and years about that. But we developed this code. It's running on a petaflop machine. I will flash it by in a moment because it's computationally very intense. Each of these data sets, when they come in, are 0.1 petabyte. We reduce them further down and then process them in parallel, calibrating in 122 different directions for every times slot in every frequency. And they're all connected to each other and regularized as well. So it's a very large optimization problem. So when you do that subtraction for the bright sources, you reduce this very crowded field to something like this. Of course, you still have residuals and sources that are too faint to subtract. So we'll deal with them in a different way. This is somewhat higher resolution. If you look at it at somewhat lower resolution, shorter baselines, you're completely confusion limited. So at that moment, you can't really subtract things anymore. So we use different techniques like Gaussian process regression then to remove this, using the fact that the galactic foregrounds and all the sources, etc., are spectrally smooth. So we are dealing with something like this, right? And still, right, this is in millijansky. So our signal is roughly still 3-4 orders of magnitude below that. So this is the two-dimensional power spectrum of those fields. I haven't really talked about this, but we take then a data cube, and as I said, right, frequency is also a third dimension, so we turn everything into effectively a three-dimensional cube, Fourier transform that, square it, and then average in annuli as function, and then also Fourier transform in the frequency direction. So that means that this is the Fourier transform in the spatial direction, then this in the frequency direction. Now, of course, for an isotropic signal, whatever you would see here should be sort of isotropic, right? It should be sort of circular here. But you don't see that because you still have those galactic foregrounds in them, and they are spectrally smooth. So they should be living here. And what you see here is what we call a wedge that is instrumental. We can explain this as well. Okay, so that's where we are. I think I might have skipped one. No, I don't. So we have now published these results in 2020. We have set, right, just barely up limits. We are now starting to exclude the most extreme astrophysical models. So you can read up on this, but I would like to quickly go on to things that we've done recently. And of course, since 2020, we have done a lot on our systematics. That has been the name of the game. We've developed a pipeline now that I asked my postdoc to write into a pipeline that even a monkey can use. So we have it now, right? So that means it's much, much easier now to use on the petabytes of data that we will process in the coming years on this new GPU cluster. It was a misery to get during the chip crisis. So this is the latest results. We're writing this up at the moment. So this is what we published 2017. This is what we published in 2020. Now this is exactly the same data, but we're deeper, and we're also going now for 3 redshifts. So not just single redshift, 3 redshifts. As you see, we're not at the thermal noise yet. We call that excess variance. And again, I can explain to you what that is. Now this excess variance, right, as I said, we have 2 fields. So recently we looked at another field. This field is 3C196. So it's seen here, this is the NCP. So it's away from the NCP, but it's also further away from all these bright sources. And if you now look at this field, it actually turns out it has less of that excess variance. So the more yellowish, light yellow it is, the better it is. So this looks better than this. And that is, we think, because of this leakage of bright sources via the side lobes. So it's very important which field you choose, and we now know that this excess variance is dominated by bright source leaking in via time-varying side lobes. So we have a very good path forward to mitigate this. For example, on this same field, we go much, much deeper than on the single night on the NCP. So this is very promising. We now have 2 fields that we will process in the coming years. So very quickly to nanofar, because I'm running out of time. So this is really focusing on the cosmic dawn. We do exactly the same. We can use this right pipeline for monkeys to run this. Really, literally, we took this data on day 1, we ran it through the pipeline, and we immediately got an image. We didn't have to change anything to our software for this new telescope. So we have now published the first upper limits there as well. Again, it's dominated by excess variance. And again, we can explain this because if you look at that field here, this is the NCP field, the one I showed. If you look at the really dark patches here, these are different fields. This is leakage from side lobes of these bright sources. You see that the darkest fields are also the darkest here. So we really know that also here we're dominated, right? NCP versus these look much, much more clean than this. This is side lobe leakage. So again, where we are now. So what's the next frontier? This is about frontiers, right? So the next frontier is really about SKA. And SKA is being built as we speak, SKA low. Of course, there is part of SKA mid already, right? In March 2024, first dipoles went up. I think there might already be a few stations, at least 1 station completed in Australia. And of course, this will be a transformational instrument. Again, right, we have done all the groundwork with LOFAR, nanofar, right? Even if we get very close, we feel a signal, right? With SKA, within matters of hundreds of hours, we will get a detection and maybe even see bubbles. The sensitivity is enormous with this instrument. Right, so this is the sort of signal to noise of 100 you might expect after even 10 to 100 hours with the SKA over various, this is 1,000 hours if instantaneously, and if you do surveys over with 10 hours per pointing, you get signal to noise of about 100 at all EOR redshifts on the power spectrum. You can get all these astrophysical parameters. And recently we used our pipeline in a blind challenge from the SKA offers, and we came out #1. So our pipeline actually detected the signal they had injected with all the foregrounds and errors, etc. Of course, tomography is ultimately what the SKA is all about. Right? When SKA was being built and they had to cut back on the cost, there was be something between 2 times LOFAR and 8 times LOFAR. And they said, well, 2 times. I said, well, I'm not going to spend 30 years of my life building something twice LOFAR. Give me the money and I double LOFAR. Right? So I said, we need 8 times LOFAR, then we can do bubbles. Right? I don't want to do error bars on error bars for the rest of my life. So this is what SKA will really be transformational about. Now, talking about the final frontier is the dark ages. We haven't talked about that yet. Why? Because you can't do it from the ground. The ionosphere will stop you doing this. The ionosphere kicks in at 10 or even beyond that. The effects are so strong that the signal will be heavily distorted. So you have to go to the moon. RFI is another huge problem at those low frequencies, and stability. So everybody has identified the moon, either in orbit or the backside of the moon, as the ideal site. So there are many experiments, including one of us that I will show in a moment. This one, for example, is already flying since 2018. It's a Dutch experiment on a Chinese relay satellite. Unfortunately, it had some technical problems, but there is something there. And then over the last few years, together with ESA, we have done a CDF to develop this report of 300 pages on an instrument that we want to put on the moon in the coming decade to go for the dark ages. It will be a very compact array, phased array, compact, large. Larger than SKA ultimately, but ultra compact and FFT type telescope. So not the standard correlated telescope, but an FFT telescope. We make instant images every millisecond. And you can do that with your iPhone almost. The Fourier transform of that size is not difficult. This is what it looks like. These are not, of course, photographs. These are computer generated. It's not there yet. We are identifying sites, probably in craters on the backside of the moon, to shield it. With the Lunar Reconnaissance Orbiter, we can look at those orbits, those craters, and you can find areas which are extremely flat. If you put it down there, it's like a flat surface. The wavelengths are very large. So we can find areas where to put them. And ultimately, with an array of merely 10 square kilometers or so, and thousands of hours of integration, we should be able to get these kind of signals at redshift 40 or 50. Now we're talking about the 2040s now. Now, of course, the race to the moon is on, as we all know. I put some of these pictures under the right angles. Right, so this is the Japanese one upside down. This is the American one that fell over. I haven't put the picture of the Russian one on. It's just a crater. But China is there, of course. India, we were there. So this is not just for us, right? There's a real drive to the moon, and we're piggybacking on that drive. So what's next? You can read that up when the slides probably go online, and I will stop here with my summary and conclusions, which you can read. And I thank you for listening.